mechanical energy. Just like the name mechanical energy, it is almost looking like a machine. So when we talk about mechanical energy, basically what we're talking about is simply kinetic energy and potential energy. Remember, we defined kinetic energy as the energy possessed by a body by virtue of its motion, or any body in motion possesses kinetic energy, and any body at a point in a uniform force field possesses potential energy. So when defining mechanical energy, we use both of those two definitions there. In other words, mechanical energy is the energy that is possessed by an object due to its motion and due to its position in a uniform force field. So from this definition here, we can see that this is actually kinetic energy, and this is actually energy due to potential energy. In other words, mechanical energy is the sum of both kinetic and potential energy. So, after having looked at those two terms there, comprising of mechanical energy, then what is kinetic energy in details? So kinetic energy is the energy a moving body has, and it is given by a formula: a half times mass times the speed squared. In other words, it is a half mv squared. So just note that the v does not mean the velocity, but rather it means the speed, and therefore kinetic energy is a scalar quantity. Also note that the direction of motion has no relevance to the kinetic energy. That is what I've just said, that kinetic energy is a scalar quantity. All energies are scalar. We don't mind about the directions. So at the moment, we need us to remember that kinetic energy is always given by the formula a half mv squared. Let's try an example here. So for example, we've been given that calculate the kinetic energy of a car of mass 800 kilograms moving at 6 meters per second. So the first thing to do always, whenever you're going to calculate for anything, always summarize the question first. So we've been given the mass as 800 kilograms, and then the speed as 6 meters per second. So remember also that in case we're going to calculate for anything, also try to write down the equation of that. So kinetic energy is given by a half mv squared. So we have everything. What we need to do is just to substitute, and everything is in SI unit. So kinetic energy is a half mv squared. Our mass is 800. Our velocity is 6. So in square and substitute into the formula, we shall get that our kinetic energy is equal to 14,400 joules. Number 2 says that calculate the speed of a car of mass 1,200 kilograms if its kinetic energy is 15,000 joules. So in this case also we've been given that the mass m is equal to 1,200 kilograms. We've been given that the kinetic energy is equal to 15,000 joules. So at calculate for the speed v. So remember that kinetic energy is given by a half mv squared. When you substitute into that, what you need to get is the v. So which means therefore that substitute kinetic energy and the mass, and then get your v as shown here. So the final velocity v of the car is 5 meters per second. Number 3 says that calculate the braking distance a car of mass 900 kilograms traveling at an initial speed of 20 meters per second if its brakes exert a constant force of 3 kilonewtons. Calculate the braking distance. So in the question, they want us to get the distance s. We've been given the mass as 900 kilograms. We've been given the initial velocity u as 20 meters per second. And then we've been given the braking force as 3 kilonewtons, which is the same as 3,000 newtons. So since we're looking for the velocity, for the speed, for the distance s, then it means that we have to review our equations of motion. The first one is v is equal to u plus at. In this case, there is no distance, so you cannot use this equation. The second one is s is equal to ut plus a half at squared. In this case, there are two unknowns, the s, the distance, and then the time t. So meaning that this equation 2, in order for us to use it, then we must be knowing at least the time. We can get the acceleration from F is equal to ma. We have the initial velocity, but don't have the time and then the distance. So the third equation is v squared is equal to u squared plus 2as. So using this equation, the third equation, since we have the initial velocity, we have we can get the acceleration, we can get the distance s. So what we do here is if we are to use the equation, we shall use v squared is equal to u squared plus 2as, but still we don't have the acceleration. Let's begin by getting the acceleration. So from the equation of force, Newton's second law of motion, F is equal to ma. The force is 3000, the mass is 900. Substituting to F is equal to ma, we shall get our acceleration as 3.33 meters per second squared. There's per second squared here. And recall that this is braking force. It is the braking force, meaning that our acceleration is actually going to be equal to a negative. The force is negative, the acceleration is negative as well. It is decelerating. So after having got the acceleration, then from our equation v squared is equal to u squared plus 2as, if the braking distance, we are going to assume that if the braking distance is what we're looking for, then we're going to assume that the final velocity is 0. So from our second equation, from our third equation of motion, use v squared is equal to u squared plus 2as. When we substitute into our final velocity is 0, the initial velocity is 20, and then the deceleration is given there. So substituting into this equation will give us our distance as 60 meters. Let's look at gravitational potential energy as well. So from what we've just discussed already, gravitational potential energy is the energy possessed by a body at a point in a uniform gravitational force field. In this case, we are particular with gravitational force field because we are talking about gravitational potential energy. There is also what we call the elastic potential energy. In that case, the force field is elastic forces. So gravitational potential energy is the energy an object has because of its position in a uniform gravitational force field. And it is given by mass times gravitational field strength times the change in the height. In other words, it is mg H. That is the equation for gravitational potential energy. An example is calculate the change in potential energy when the mass of 200 grams is lifted upwards by 30 centimeters. So look at this. This is grams. So we're going to change this one to kilograms, and that is 0.2 kilograms. And then 30 centimeters, changing it to meters will give us 0.3 meters. So from the equation of potential energy, mgh, the mass is 0.2, the acceleration gravity is 9.81, and then the change in the height is 0.3, and the answer is 0.57 joules. So after having looked at kinetic and potential energy, there is also what's called the principle of conservation of mechanical energy. Remember previously we've just looked at the principle of conservation of energy, where we say that total energy in a closed system is always a constant, or energy is neither created nor destroyed but simply changes from one form to another. So if you're talking about the principle of conservation of mechanical energy, and we've just said that mechanical energy is kinetic energy plus potential energy, it means that in a case a body is moving from one place to another, maybe the height is changing, the height is rising or it is falling, then there are only two energy conversions. We assume that all the other forces are negligible. For example, there's no air resistance and so on. So we shall simply say here that the total mechanical energy in a system is always a constant. So we shall state our principle of conservation of mechanical energy as the total mechanical energy in is a constant provided that no dissipative forces act on the system. And the dissipative forces are those due to friction, air resistance, viscosity, drag. All those ones are dissipative forces. In other words, they retard the motion of any body. So, in order for us to prove this principle here, there are two ways. We can either prove it when the body is thrown vertically upwards or when the body is falling vertically downwards. So to begin with, let's look at falling bodies. The proof for conservation of mechanical energy for a body falling in uniform gravitational field, we're going to assume that in this field here, there is no any other external force acting on the system or on the body apart from that due to gravity. In other words, there is no air resistance or something of the kind. So what we're going to do, we're going to begin by assuming that we have our body at point A, and it is at a given height from another point which we shall call C. At given height H, I'll call it H. And we can create another point B in the middle or in between along its motion at any point, and that point B is at a given height. I'll call it H1, like this. So at this point here, at this point A, assuming that the body is at rest, in other words, it means that the initial velocity u is equal to 0 meters per second. And since we are proving the principle of conservation of mechanical energy, and whether the mechanical energy is the sum of potential energy plus the kinetic energy, we're going to be getting the expressions of potential energy, then the kinetic energy, and then we add them together and we see whether we shall be getting the same expression at all the 3 points A, B, and C. Now, since the body is falling, we shall get the initial expression of mechanical energy in terms of the potential energy, as we are going to see here. So at A, the potential energy is given by mgh, because the height from the ground is the h. And then the kinetic energy is given by a half mu squared. But remember that our u is 0, which implies that this is the same as a half m times 0 squared, which will give us 0 joules. So this implies therefore that the mechanical energy at that point A is given as mgh and then plus 0, which will give us mgh, like that. So that is at point A, which means that if you've got our initial expression as mgh, then we have to prove that for all the other points B and C and any other point that will create there will be given in the same expression as mgh. So let's try it out and we see at point B. Assuming that the body has fallen and at this time round it is at point B, the potential energy at this point B is given by mg times the height h1. Remember, we measure the height from the bottom going upwards. Don't say that it is h minus h1. No, it is the height from the ground up to that position there. So that is mgh1. And then the kinetic energy at this point is given by a half times the mass times the velocity at that point B, but I square this. So remember that from the third equation of motion, our v squared is equal to u squared plus 2as. And since the body is falling, the velocity at point B squared will equal to the velocity at A, which is our 0 squared, then plus 2. Now the acceleration is that due to gravity, and it is a positive because the body is falling downward. So I'll simply put here my h, and then the distance moved through from A to B will be is going to be equal to the h minus the h1. In other words, from this point here to this point here, the height will be equal to h minus h1. So substituting this into this expression of kinetic energy, we shall be getting that our kinetic energy is given by a half m into velocity at B squared, we shall be having 0 squared plus 2gh, then minus 2gh1. So when we simplify this, we shall get mgh minus mgh1, and this is our expression 2 at that point B. So at B, when I add the two equations, Roman 1 and Roman 2, I will end up with mgh1, that is potential energy, and then mgh, then minus mgh1. So these two here cancel out, and we shall end up with our mechanical energy being equal to mgh, and that is our equation 2. So doing the same for our body at point C, we shall simply do this. So continuing with the same at point C, we shall simply see that at point C, the body has moved through a given height h, and it is at the ground level or the reference level where the height is 0. In other words, at C, so our potential energy is given by mgh, but this h here is equal to 0 because the body is at this point here. The height from the ground to that point there is 0. So implying that our potential energy is 0, and our kinetic energy, which is equal to half mv at C, but squared. But remember, still from the third equation, v squared is equal to u squared plus 2as. We shall simply have it that the velocity at point C, when you square that, the initial velocity was 0, you square that, then plus 2, the a is the positive g times g, then times the height moved, that is the distance moved, that is the h. This will give us our kinetic energy being equal to a half m into 0 plus 2gh. And when expand this, when you simplify this, sorry, you'll simply have this as mgh, and that is our Roman 2. So which implies therefore that at C, the mechanical energy, which is the sum of the potential energy plus the kinetic energy, will give us the expression as mgh, and this is our equation 3. So comparing the three equations at point A, B, and C, the mechanical energy is given as mgh at A, is given as mgh at B, and mgh at C, which therefore implies that mechanical energy is conserved. Remember, we are expressing everything in terms of the initial mechanical energy, which was at A, since the body was falling. Thank you very much. Enjoy. Please subscribe the channel and visit us at teachertaban.com. Let's also try to prove the principle of conservation of mechanical energy for a body that has been thrown upwards. All right, so this time around, we want to prove the principle of conservation of mechanical energy, which says that the total mechanical energy at any given point in a uniform force field is a constant, and T0 is given by potential energy plus the kinetic energy at that point there. So I want to prove this principle here when the body is rising upwards. In other words, when the body has been thrown vertically upwards or at an angle, whatever, so long as it is rising upwards. And in the same way, we shall assume that there is not any other force acting on the system apart from that due to gravity. In other words, there is no air resistance and any other resistive forces or dissipative forces. So in the same way, let's consider 3 points, points A, B, and C in the middle. C, let me put B in the middle here, and the distance between A and C is our height h. The distance between A and B is our height h1, and the body is at this position here initially, and it has been given a velocity v upwards. A velocity v upwards. You can use u, it is okay. Actually, let me even use u. With a velocity u, meters per second. At this point A, the body is at its initial reference point, meaning the height h is equal to 0, meaning therefore that our potential energy is given by mgh, which is equal to mg times 0, which will give us 0 joules. And then the kinetic energy is given by a half mv squared, mv squared, but remember we have used our u, so I'll leave it in terms of the u, a half mu squared. Now these two, when you add them, they'll give us the mechanical energy, which is 0 plus the a half mu squared, which will give us a half mu squared, and this is our equation 1 at point A. Now, since the body is moving upwards, and our initial mechanical energy that we've got is in terms of the velocity u, it means that at all the points B and C, our final expression of the mechanical energy must be in terms of the u as well. In other words, the mechanical energy must be equal to a half mu squared. All right, so let's check this out at point B. So at B, the body is having a potential energy which is equal to mgh1. Remember, the height is measured from the ground up to that point B. So that is the expression of potential energy. Then kinetic energy is given in terms of velocity, which is a half mv squared. But this v is the velocity at this point B. Is the velocity at that point B there. And remember, we have to express that, we have to remove everything like the h. We have to get that velocity v in terms of our initial velocity u. So what you're going to do is that since we added these two and remain with the h, we have to look for a way of eliminating this h in the potential energy. And how do you do that? We simply use the equations of motion, and from the third equation as well, that velocity at b squared is equal to the initial velocity squared, then plus 2as. Now, since the body is moving upwards, it is moving against gravity. So the initial velocity remains u squared, then plus, it's a 2, the a becomes minus g, and the distance moved upwards is the h1. So this is the same as u squared minus 2gh1. So substituting this one into this expression, we shall have our kinetic energy as a half m into u squared minus 2gh1 in brackets. And when expand this, when you expand that, it will give us a half mu squared minus mgh1. So this is Roman 2, this is Roman 1. When you add the 2, we shall get that at point B, the mechanical energy is equal to the potential energy, which is equal to mgh1, then plus kinetic energy, which is equal to a half mu squared, then minus mgh1. And when add up all of those, we shall get the same expression as a half mu squared. That is our equation 2. All right, let's do the same at point A. At point C, and see whether we get the same expression here. So at A, I'll simply say that my potential energy is equal to mgh, then the total height is h. And at this point A, we're assuming that the body is at maximum height. At maximum height, the velocity is always equal to 0. So meaning that our kinetic energy is equal to a half times mv at c squared, which is equal to a half m times 0 squared, which will give us 0 joules. And our velocity at point C, from the third equation of motion, v squared is given by u squared, then plus 2as. That is from the third equation of motion. And we just said that velocity at C is 0. Our u remains as it is, plus the 2, the a becomes minus since the body was moving against gravity, and the distance moved upwards is the h, implying therefore that our h is actually equal to u squared out of the 2gh. So when we express this into this equation of potential energy, we shall simply have it that potential energy is equal to mg into u squared out of 2gh, and therefore the potential energy will be equal to a half mu squared. So therefore at point C, the mechanical energy is equal to a half mu squared, and then plus the 0, which will give us a half mu squared, and that is our equation 3. So we've proven that the mechanical energy at points A, B, and C, since the body is rising up, shall give it in terms of the kinetic energy, and it is equal to a half mu squared, and this proves that mechanical energy is conserved. Please check out the video here, subscribe, like, share. Let's study together at teachertaban.com. See you.